right, so let's now take a look at the reminders. Again, let's now revisit the course calendar right here. Okay, so we are now here on the 10th of March. So we're going to cover, including today, 2 more lectures, and that should be enough for your written test coming up, right? Not this coming Thursday, but next Thursday, the 19th of March, there will be your written test. And please also notice that your programming test 2 will just come after that next week, right? That's something we already announced on day 1 of the course. Just make sure you plan your time accordingly. And before your Thursday class, I will release a PDF guide talking about the coverage and format and also some practice questions for you as well for written tests. I'll try also to release your programming test 2 guide also a little bit earlier so you guys can know how to practice. But I think the expectation will be very similar to programming test 1. So if you do similar preparation accordingly, but of course with respect to assignment number 3, and I'm going to post assignment number 4 as well, I think you should be okay, right? So please watch out the deadline for your assignment number 3. It will be next Monday, all right? So make sure you do that before the class. If you can submit earlier, submit earlier. I'll also give you guys solution as soon as the deadline passed. And assignment number 4, which will be more like a continuation of A3, just give you more examples about how you can work with trees. I think that one there is also going to help you on programming test 2, right? I can even release the solution for assignment number 4, maybe even earlier, so you can also take a look at the solution. So that might be to your advantage. We'll see. All right. All right, and then again, the makeup lecture for your programming test 1 is being released for a while, so make sure you plan your time to watch that and study the contents. And there will be another makeup lecture coming for your written test, right? Accordingly, right? That's something I'll release also in time, so you can also get started with that. All right. So any questions in general about the course? All right. Yes. In the written test, right? Yeah. Okay, let me confirm when I release the guide. Okay, I'm not exactly sure. I gotta check back to what I have at the moment. But I would say no matter what, you definitely want to get started with the makeup lecture, right? It's definitely important, yeah. Okay, yeah, I'll confirm the exact coverage about your written test for sure before Thursday's class, yeah. Okay, any other questions? Again, if you got any concern, you want to discuss progress, strategy about studying, or even the final exam, programming test 2, you're more than welcome to speak to me. I still got office hour this week on Thursday. But if you really cannot make it, email me. We can make time. We can arrange some time at your convenience, right? We can talk about it. But you got to reach out first. Otherwise, I wouldn't know if I can help you. All right. Okay, so let's do a quick recap from last time, and then we're going to continue. So last time we started with this geometric sequence sum over here, the formula, right? So this, of course, I will highly recommend you try to really study the derivation process. So in case you forgot exactly how the formula should look like, because in the written test and also in the exam, you don't really have a data sheet to be brought together with you. So you may either want to maybe memorize the formula. Of course, that's one way. Or you want to make yourself ready in case you have to recall the formula by deriving it, right? That'll be my recommendation. Okay. But overall, this will be the general form of the formula about k terms. But specifically for binary tree, we got initial term will be the root, just a single root, single node, which will be 1. And also we got every node has maximum 2 child nodes. That's why the common factor will be 2. If you simplify the formula accordingly, you got 2 to the k minus 1. And the k here will be very common, h plus 1, where the h will be the height of the tree. All right. And then we derive about how many, depending on how many levels you have in the tree, what will be the maximum number of nodes that's contained in the tree. So this formula here, the final outcome, 2 to the k minus 1, or accordingly, right here, 2 to the h plus 1 minus 1. That one is going to help us also understand about how we can bound the number of nodes in the tree in the minimum and also maximum case. So you want to also make sure you know how to derive such thing from scratch. All right. Guys, any question about this page? That one I would say arguably the most important page from last time. Okay? Okay. And then we talk about the difference between complete binary tree and also full binary tree. Complete binary tree, of course, you can go back to the slides for the 3 criteria for defining what a complete binary tree is. Basically, first of all, you got to consider the bottom level at depth h. You got to consider the second last level at depth h minus 1. And then you got to consider the third compartments starting from level 0 all the way to and including h minus 2. Right? So these are the 3 different parts. You have to make sure they all satisfy the criteria for being a complete binary tree. Accordingly, we try to compute what will be the minimum and maximum number of nodes in the complete binary tree. Right? Of course, the minimum case will be you got only 1 node at level h. The maximum case will be you got exactly 2 to the h at bottom level, level h. Right? And the full binary tree is more like a special case for a complete binary tree where you simply got the maximum number of nodes at level h. Right? So you can think about these two are very related, but you should really get yourself familiar about which is what. Right? And that's just a visual comparison about the two, right? Complete binary tree, full binary tree, right? So here you got some range, but here you don't have a range. You only got one choice. Minimum, maximum are just the same. And this one here is just about the third criterion for complete binary tree. You have to make sure the bottom level here, level h, the nodes will be arranged from left to right. You should not really skip any nodes. For example, here, this will be a left child. So if you do have another node at the bottom level, it should be the right child of the same parent nodes. But in this case, I got left child, but I don't have a right child for the same parent node. And I simply got the next node being the left child of another node. So that's not satisfying the definition for the complete binary tree. So in the written test and also in the exam, you want to be ready to really recall the 3 criteria for a binary tree to be complete. And also, if I give you any example or counterexample, you ought to be able to judge against the criteria. I think that these would be the basic I will expect. All right, clear? Okay. All right, and then we talk about binary tree properties. We finished 2 of them about bounding the number of nodes given the heights and binding the heights given the number of nodes. That's something we did. So I'm gonna skip that for today. Right? You're gonna review the notes and also recording if necessary. I just want to talk about another 2, which are pretty much the same as counting the number of nodes given h. Very similar, right? We just have to review the same diagram by counting different parts of the tree accordingly. That's something we got to do. All right. All right. So these 2, I'm going to leave them to you. Right. The little derivation we did last Thursday. I think this is a very beautiful derivation based on what we know already. So you want to get used to about log. I think you might need that also in the written test and also the exam. Okay. All right, if no question, why don't we go on to the first bit, right? Let's finish off the final 2. Oh, one more thing to say. So this page here is also very important. If you recall, let me show you very quickly, right? I think in an earlier lecture, we spoke about how you can define a generic tree in Java. Specifically, you can see here, I'll show you exactly what I'm referring to. Let's say we got a tree node, and then every tree node has an array of tree nodes being their children, right? So in this case, we're using an array, as opposed to in the assignment, you're using a linked list of the tree node. So you ought to know both, right? Both are valid way to implement this stuff in Java. And this one here, the only workaround you have to be aware is when you try to initialize a children array, which is generic right here, and the generic parameters wrap within the tree node class over here. So that means you cannot really just use the normal initialization and do some typecast. It's not going to work, right? That's something I want you to go over in the exercise to make sure you understand about how this line here can be written. That's also very important. So where can you find it? Okay, I'll show you. So that's the context. And this page here, I'm going to leave it clean. You can maybe study just about 10 or 15 minutes to study this part. Okay, I'll show you to you how you can find it right here. Okay. So if you go to the lecture site right here, and you will see that right here under exercises, right here. Okay, under exercises, you will see that the second exercise, initializing a generic array in Java. If you click on that, it's more like a solution video to walk you through about why that particular workaround for Java code. If you didn't follow that, very likely you will run into the class cast exception, which you guys learned back in 2030. All right, so this part here, I'm going to leave it to you. About 10 minutes to really walk you through. Make sure you also get ready for that part. Okay. All right, and let's now talk about two more properties, and then we'll move on. Okay. And it's really about bounding the number of external nodes and also bounding the number of internal nodes. Guys, quick check. What's the difference between external versus internal nodes? Basic definition. Anybody? Would like to try? Please.
External has no children, but internal has.
At least one children, exactly. Thank you so much. Right? Your fellow student was exactly correct. So external node case and internal node case, the shape of the tree we're going to consider will be just the same. Okay? So let's see. Okay? I'll make it right to the point. So here we are saying that given a binary tree and given a height h, we're going to use some example to illustrate. The minimum number of external node will be just 1, and the maximum will be 2 to the h. All right, let's see how we can visualize this. Okay? Let's say given that the height is 3. We know that when the height is 3, the minimum number of node case will be a slanted tree, right? So let's now draw that, and then we can work out accordingly. So when height is equal to 3, right? Let's take this example here. So I have the root, and then I want to draw the minimum number of nodes to reach to depth 3. Right? You can see that's exactly 1, 2, and 3. Right? I got a minimum number of nodes. So now you can think about, in this case, we only worry about external nodes. How many? Well, just at the bottom here. That's the minimum. That's the only external nodes you have. As easy as that. All right? So that's why you will see 1 right here. How about in general? In general, very similar, just depending on how high the tree is. Okay? In general, we can think about you have the root, and then you go on all the way to the bottom right here. And then we are really talking about number of edges that you have. The number of edges to really go from the deepest node all the way to the root is exactly equal to h, right? In that case, the only external node we have is the bottom one. That's the only one. Other than that, every other node has exactly 1 child. Right? In that case, it's not external. All right. So this will be the external nodes. External node. So minimum case is very straightforward. Okay. What about maximum case? Maximum case, we basically want to result in the maximum number of nodes and to reach the heights h. Again, let's now look at 3 here. And that's something we drew earlier, right? So let's take this more like a recap. Okay, so we got, this will be depth 0, and then we reach to depth 1, and then we reach to depth 2. And since we talk about 3, 1 more level, and then like that, right? That's something I am pretty sure you know how to draw. So this will be exactly 3. And when we try to count the number of internal nodes, beg your pardon, external nodes, it will be all the nodes at the bottom here, right? So here we can use our little formula, or we can just count in this case. It will be 1, 2, 3, 4, 5, 6, 7, 8. But that one, no surprise, corresponds to 2 to the 3. And the 3 here is just the h, which will be 8, right? So the maximum number of nodes you can have at a particular level will be 2 to the h. Right? That's also something we said last time. Okay? How about in general? In general, we have a binary tree that's full, basically. You have a full binary tree. Right? You got to recall the definition for what a full binary tree is. And we talk about how many nodes we have at the bottom level, right here. So we got level 0 all the way to level h. And according to what we said earlier, this should be 2 to the h external nodes. These are the only nodes without any children. All right? All good? Good. All right, let's now basically talk about the same structure for the tree, but let's count the remaining nodes because any node that's not external should be internal. Let's count them, right? So similar case. If you want to count the minimum number of internal nodes, it's still the same slanted tree. Let's do that first, okay? So let's say we still have, let's go with example. Always go with some example, just to make yourself more intuitively comfortable. So 1, 2, and 3. And we said earlier, the bottom one here is external. That means the remaining ones will be internal, right? That's obvious. So think about all these are internal. Internal nodes. And let's make it a little bit more precise, right? There's something I also mentioned earlier, but let's now repeat. The observation. You basically are thinking about if you got a chain of nodes, you basically got interleaving, okay, let me show you what I meant. You basically got interleaving node and link, node and link, node and link. This kind of structure. The number of nodes will be exactly one more than the number of links, right? Let's now write it down. And then we can use that observation to derive the general case. The number of links, which will be just the H. 1, 2, and 3. All right? And then the number of nodes. The number of nodes will be the number of links plus 1, which will be 4. And that makes sense. 1, 2, 3, and 4. All right? And we know that out of the 4 nodes, only 1 is external. Minus 1, you get 3 internal nodes, right? Sounds very trivial, but let's write it down because we can use that to verify. Okay? And the number of internal nodes will be number of nodes minus just the 1 external node, which will be 4 minus 1 and will be 3. Okay? Yeah, hopefully you can still see that, right? Okay, good. And let's talk about in general. In general, if I have a slanted tree, start from the root, all the way to right here, right? The bottom level here, okay? So here I have the number of links will be H, right? That's the height of the tree. And then we can now say the number of nodes will be the number of links plus 1, right? Pretty much like where we got 1, 2, and 3, number of nodes plus just 1 to get the nodes. And finally, out of the H plus 1 nodes, only 1 is external. The remaining one should be internal. Okay, this will be H plus 1. Okay, so finally, the number of internal nodes will be the H plus 1 in total minus 1, which is the external node we have. That will give us H, which is the H right here. Very subtle, but you got to be precise, right, when you count. Okay. All right, how about maximum? Maximum, we're going to consider full binary tree. Okay. Again, let's now draw that. So I have, let's say, again, start with 3. Depth 1, depth 2, and also depth 3, right here. And this time we're counting anything that's not external, which will be everything except the bottom level. So think about it's right here. This part here will be all the nodes that are internal. Okay? So these are the internal nodes, which will be 2 to the 0, 2 to the 1, 2 to the 2. All right, if you do the math, it's going to be, in this case, well, I'll write it down. 2 to the 0, 2 to the 1, plus 2 to the 2, right? It's going to be just 7. Okay, what about in general? In general, we're going to go back to our geometric sequence sum. I'll draw it here. In general, right here. Let's say the height of the tree is H. And then, oh, beg your pardon. And then over here, the bottom level here are all the external nodes. So these are 2 to the H external nodes. And this part here will be all the internal nodes, this part here. These will be internal nodes. But now the question is, how many? All right, so let's now apply geometric sequence sum. The bottom level will be level H. The second last level, which will be the last level for internal nodes, which will be H minus 1, and then H minus 2, all the way to level 0. Right? Let's now do the geometric sequence sum. It's going to be 2 to the 0 plus 2 to the 1 plus all the way to the last level for internal. That will be 2 to the H minus 1. All right. The other one is going to be basically 2 to the K minus 1. And the K here will be the number of turns we have. So we go from 0 all the way to H minus 1. We got H terms, right? So that'll be 2 to the H minus 1. So that'll be the final outcome. 2 to the H minus 1. I'm going a little bit fast because that's really something we went over already in the previous lecture, right? That's something you should really review and make sure you're able to be smooth like this in the test or the exam. Okay? All right, guys, any questions about this? James, you okay? Okay, I want to be sure. Good. Okay. All right, so that's about mathematical properties for binary tree for now, but please make sure you study for that. They are not difficult, but you got to make sure not just to only understand on the paper, but you really want to know how to derive them. Okay, I think that's the most important part. Okay. All right, let's now see what we should cover. Right. So we are done with slide number 33 and 34. Okay. All right. And I would like to do something also very important. It's not the primary focus for this course, but I think it's a necessary component. We'll do more about such a correctness proof, which I'll show to you in 3101 algorithm. But I think we can at least do one example to give you the idea, right? Which is important. Let's now introduce some terminology first. Okay. Proper binary tree. Okay. So we talk about full binary tree. We talk about complete binary tree. This is another term, proper binary tree. By definition, every internal nodes, any node that has a children, must have 2 children exactly. So basically either 0 child, which is external, or 2 children. Cannot be 1, basically. All right? So that's the definition for a binary tree to be internal, to be proper. Okay. And that's one example here, right? Let's just see from the slide, and then I'll try to do a little bit more annotation. You can see in this tree here, we got external node. Yes, you can see this is one external node, has 0 child. And this is just another external node for 0 child, right? On the other hand, every internal node in the tree, for example, the root over here has exactly 1 and 2 children. And this internal node, for example, here also got 1 and 2 children. If you apply the definition, every node that has a child, at least 1 child, got exactly 2 children. Cannot be 1. If you have a node that has only 1 child, it's not proper binary tree anymore, right? Given this definition, what we'd like to do is to prove some nice property about this kind of a binary tree, right? That's something we're going to spend some time on today, okay, in the first half, okay? Okay, let's now take a look at this property here. So given a binary tree, okay, let's go over just a few more bullet points and then we'll move on to iPad, do some visualization. Given a binary tree, first of all, it's not empty. We got at least 1 node in the tree. And it's also proper according to the definition we had, okay? Given that. And we have 2 counters. One counter is called n with a subscript I, the number of internal nodes in the tree. We got another counter n with a subscript e. That'll be the number of external nodes. Okay, given these, we want to show that the number of external nodes will be the number of internal nodes plus 1. All right? We want to show that for any tree that's proper and not empty, this equation here should always hold. The most rigorous way to really show this property here is by something called mathematical induction. All right, so let's now try to do that from scratch. Okay. Let me just very briefly review or introduce about what mathematical induction is more like a proof strategy, what it is like. Anytime you want to prove some structure, prove the property of some structure that's recursive, notably tree or later on graph, mathematical induction is definitely the way to go, right? Whenever you want to prove something formally. Okay? So let's now start with some very brief facts about mathematical induction. You will see the skeleton for the proof. So we start with mathematical induction. Mathematical induction. Okay. And to see the proof, typically there will be several parts you will need. Okay, part number one, base cases. Oh, by the way, so you can also try to relate mathematical induction to how you program recursions in any programming language. Very similar. You got to think about base cases, you got to think about recursive cases, you got to think about how you can combine the two somehow, right? We'll see. So a little bit quite relatable to recursion, which is not surprising. Mathematical induction is really supposed to prove anything with the recursive structure. So it's just like a recursion. The first part will be base cases. Let's say there is a property I want to prove. Okay, think about the P here is a property I want to prove. So property to prove. Okay, and base case is to say the property should really hold on smaller instances. So let's say the structure is simply just empty. Example could be maybe it's an empty tree. For example, empty tree, or it could be empty list, empty collection basically. Think about we want to prove some property for some arbitrary size collection. The base cases will be when the collection size is very small, notably 0 and 1. That's typically, that's usually the common base cases. We can also show P of 1, right? So the 1 here will be there's only one node in the tree, like a singleton tree with only the root. So this would be a singleton tree with the root only. Right, base cases. I would say typically for mathematical induction, for base cases, you only have to argue 1 or 2. You don't need to go beyond that. If you want to do 3, that's okay, but it's not really necessary. If you can do the 2 base cases, that's good enough to move on to the second step. All right, first step will be base cases. Second step, which is to state the so-called inductive hypothesis as your assumption. Right? Inductive hypothesis. Okay? I might just say IH as an acronym. Right? And inductive hypothesis, well, hypothesis means I assume something to be true, so I can use it later. So we assume the property I want to prove holds on a particular collection size or tree, right? On K. And think about the K here is something that's beyond the base case, beyond base cases. Yeah, in this case, since I already argued about 0 and 1, so it should be strictly larger than 1. Okay, so here, I just say K strictly larger than 1. So you gotta prove something simple in step number 1 and assume something in step number 2, right? So these are the first 2 steps. I would say when you are seeing maybe some inductive hypothesis question in the written test or exam, step number 1 and 2 are usually more straightforward, quite routine for you to complete. Okay, But step number 3 is going to be something, I can give you an example, I can tell you insights, but it's something kind of creative. You have to just kind of adjust according to the problem. But we'll see, okay, how this problem will look like. And number 3 will be, we want to prove a strictly larger problem. Strictly larger, okay? So this will be the same property here, but I want to have k plus some constant. And the constant here can be 1, can be 2, some small constant. Okay? But let's talk about what this constant really means in general. Okay? So the C here, okay, is really the minimum extension possible that can be made to k. K is something we assume, but I want to say, what about something strictly larger than that? How can we also prove the property holding, right? That's really the essence. And one check for you. Whenever you want to show step number 3, you want to make sure, in order to complete the proof step for step number 3, you have to really use what you assume in step number 2. If you don't have to use it, there's something wrong. All right? It's necessary to make use of the claim assumed by the inductive hypothesis. This is a critical point. You just cannot just show step number 3 alone without any help. You should need the help from step number 2. Right? It's only more like an abstract strategy for you to keep in mind, right? It's more like a template or skeleton. You can see that I'm going to instantiate this pattern here for the proper binary tree claim that we want to prove. Right? Let's take a look. Okay? Any questions conceptually in general about this? Okay? Yeah, for those of you who might be taking 3101, doesn't matter which prof you might be taking with, I think mathematical induction is a very useful technique for you to know how to do, right? Especially on the graph later. Okay, so let's now take a look at this property here, right? Let's do that, hopefully, and then we'll take a short break. Okay. Again, let's now reread the question itself. We have a binary tree, and it's not empty. As soon as you see that it's not empty, think about what will be the minimum case for not empty. Can it be an empty tree? Of course it cannot be, right? Empty tree is not satisfying the criterion here. Only consider, maybe we should start considering only a one-noded tree with the root only. And then the tree you're considering should be proper. For example, I shouldn't consider, let's say, this particular tree. Is this tree proper? It's not, because internal node here has only one child, not 2. So it's not proper, right? Good. Okay, this is something we want to show. Let's use one example to show. Okay, this is a proper binary tree that we saw on the slides, right? Let's now count. First of all, let's try to count the number of external nodes, which will be 1, 2, 3, 4, 5, and 6. Okay, I'm going to write it here. Number of external nodes will be 6. And then we also count the number of internal nodes, okay, which will be 1, 2, 3, 4, and 5. Number of internal nodes will be 5. And you can see that for this particular instance of the non-empty proper binary tree, 6 equals 5 plus 1. All right, so it's satisfying. But that's not a proof, just for you to understand what exactly we are trying to build in overall. All right? And I'm just going to make this example here much smaller. Okay? And then we're going to see how we can show the property in general in mathematical induction. I do have one question for you. I think this is going to also help you see the insight for this proof. At the moment, what's the size of the tree? 6 plus 5, I got 11 nodes, right? If I want to make this proper binary tree bigger to be another strictly larger proper binary tree, how many nodes should I have as a result? For example, can I have only 12 nodes? Can I? If I want to make it strictly larger, apparently I got to create additional nodes. Let's say here, if I create one node right here, that will make it 12. But that's not proper anymore, right? Because this internal node here is having only one child, which is not proper. So it seems to me every time we want to make a strictly larger proper binary tree, we have to somehow pick some external node and then extend it with 2 children. We're adding 2 nodes, right? So the size is going to be incremented by 2 every time, right? It's a very important insight you will see when we get to step number 3 for the mathematical induction. Of course, it sounds a little bit easy because we kind of know, I know the solution already. So I think in general, what you really have to do when you're dealing with a new mathematical induction problem is to figure out some example just to convince yourself about the property and see how you can make some minimum extension and then still prove the property, right? That's a general strategy, okay? All right, let's now try to go with the mathematical induction, okay? So induction is going to be on the size of a proper binary tree. And the minimum size will be just 1, not 0, right? It's not empty. Okay, let's now work it out. Step number 1. So we're going to talk about base case. So base case will be a singleton proper binary tree. Okay, let's now draw that, right? So think about only the root. And the root should be considered as external, right? Because it has no child, right? So what we can do is the number of external nodes will be just 1. And the number of internal nodes will be, do we have any nodes with exactly 2 children? We don't. 0. Right? So that's the first base case, right? And for that one there, you can simply check to see 1 equals 0 plus 1. So the property holds, all right? So the property holds. So this single base case should be enough as far as the induction is concerned. However, I would suggest as one exercise. You can try a second base case. In that case, how many nodes should we consider? 2 or more? If I want to prove another base case, how many nodes should I consider? Exercise. That means it should be exactly 3 nodes, right? As we said earlier, right? Prove the base case on a proper binary tree with 3 nodes. All right, that's an exercise for you, okay? All right, step number 2. We're going to state the inductive hypothesis. Inductive hypothesis. And we can basically just almost like a copy from what we have over here as part of the question. So that's why I said usually for step number 1 and 2, they are rather routine. Especially for step number 2, it may not be exactly direct. You will just have to read through the problem description to really make sure what you can really copy from there. Okay? So I can say for a proper binary tree of size. Since we only so far show the base case about a single node binary tree, proper binary tree, so it should be strictly larger than 1. Okay? So it should be strictly larger than 1. And we're assuming exactly this property over here. So we have the number of external nodes should be the number of internal nodes plus 1. Okay? So let me just highlight it. External and also internal. We're saying that this here should really holds, Right? Step number 1 and 2, done. Step number 3, we want to think about how we can make the tree just larger. And then, once we make it larger, we can actually argue about if the property will still be satisfied. Okay. So here, let's now talk about the step number 3. Okay. We can continue with the step number 3 very briefly after the break, but think about what's going to happen here. If you're given a general tree that's proper, how can we extend it to be something larger? Right? That's something we already said. You can maybe pick some external nodes and convert that into internal nodes. But we're going to write it down precisely and then argue about how things will change accordingly and the property, why would it still hold? Right? Why don't we do it after the break? Okay. All right, let's now talk about step number 3. Okay. Before I write it down in words, let's think about visually, right? So here we have some proper binary tree. Okay. So this is a non-empty proper binary tree. And whenever you think about the what's really given by the inductive hypothesis, we know that given this particular proper binary tree, we have made a hypothesis about what property should really satisfy. Number of external should be number of internal plus 1. Okay, let's write it down. That's something we know already. Number of external will be number of internal plus 1. Okay, that's based on the inductive hypothesis. Right here, and also right here. Now, how can we make this tree strictly larger? And so that we can kind of use the claim from the inductive hypothesis. As we said earlier, you can pick some external nodes. Okay? So now let's imagine that this will be the bottom level of the tree. And then we pick maybe the rightmost external nodes. Pick that and then convert that into internal. So what we can do is, let's say, we can pick, let's say, this node here. Pick that one there. Okay? Pick this node here that's currently external. Let's call that n. Pick it, and then we're going to extend by 2. Meaning that we're going to create, let me just make this one slightly smaller, okay? Slightly. Oh, sorry. A little bit smaller, okay? And then that external node I pick, I'm going to extend it with 2 children. Let's say x and y. X here and y here. It doesn't really matter exactly what you pick. I just want to make it more precise. Go to the bottom level and choose the rightmost external node and convert that into internal. Let's write it down. So I'm saying that extend the current proper binary tree by converting the rightmost external node. And the node I'm talking about is n, right here, right? This n. At the bottom level. So we want to convert that into internal node. Into internal node. And by adding, of course, x and y. Right? So I think usually when you want to show your mathematical induction work, I think the safest way will be, of course, you can write down some text, but at the same time, feel free to show some visualization. I think that can help too. Okay? All right, so that's about the extension. So now we want to work out. This is the strictly larger. Oh, thinking this way. Okay, let me say it again, and then we'll get to the final step to argue about it. This part here is the tree that's covered by inductive hypothesis. and we make a strictly larger tree by including these two extra nodes. We want to make sure this extended proper binary tree is also going to satisfy this property. That's our goal. All right? But let's now make the notation more explicit. Okay? So we talk about before extension and after extension. Okay? I'm going to use the number of internal nodes here, and also the number of internal nodes ni prime. Prime means after the extension. Okay? Similarly, I got number of external nodes and number of external nodes prime, also after extension, right? So now I got 1, 2, 3, 4, 4 measures. And these two are referred to by the inductive hypothesis, okay? So let me write it down. This one here, this pair, is before extension. Before extension. And this pair over here is after extension. Now, of course, they're somehow related by x and y somehow, but we'll talk about it. This will be after extension. What's our goal? Let's state our goal. We want to prove or want to show that after the extension, this equality here should still hold, right? So that means I want to make sure the number of external nodes after extension will be equal to the number of internal nodes after extension plus 1, right? So just keep this in mind. It's very important to know what you really want to do before you actually go ahead and do it. And to show this equality here, we have to somehow use the inductive hypothesis, somehow. But we'll get to it to see how exactly we can do it, okay? And let me just put that into different sections. So now we got 1, 2, and 3. Okay, let's get number 4. Okay, let's now try to count. Number 4. Okay, and let's say we got 2 facts or claims or derivation over here. I'm gonna get number 1 and also number 2. Okay, number 1 is about counting exactly what n e prime is. Number 2 is about counting what this is after the extension. Okay, let's put it down. Okay, so we want to know what is ne prime exactly, and also what is ni prime over here. All right, let's think about what's happening here. This is the original tree, and I have converted this particular node from external into internal. So that means this is no longer the external nodes, minus 1. Also, I'm adding x and y to be the new external nodes, plus 2. Minus 1 and plus 2. Okay, will be the number of external nodes before extension, and then minus 1 and plus 2. Let me write it down. Minus 1 here is about the n being converted from external into internal. Plus 2 will be the additional 2 children I have added as external nodes. The 2 over here will be the x and y. And as you simplify, it's going to be number of external nodes before extension plus 1. Are we okay with this? You kind of count them separately. Think about what node has become from external into internal. What node has gone from internal to external. That's what you're going to do. Okay? And we do something similar. How about the number of internal nodes? In that way, you can think about this one here used to be external, but now we have converted that into internal, just plus 1. Okay? So that one, it's not as complicated. So that'll be ni plus 1. And the plus 1 over here, right here, will be just n. All right, so now we got 2 equations, 1 and 2. We're going to go to the final step, final part of the third step. Okay, number 5. All right, and this final bit here is going to be using the inductive hypothesis. If I'm able to finish the proof without even referring to inductive hypothesis, I'm not doing that correctly. Okay, what I want to show is, I want to show that this one here will will be equal to this. So let me start with the left-hand side over here. Okay, I will start with NE prime. Okay, and I know by equation number 1 right here, NE prime equals NE plus 1. Right? NE plus 1. And then I know that by my inductive hypothesis, NE equals NI plus 1, right? NE equals, by inductive hypothesis, NI plus 1. And then don't forget this plus 1, which will be, okay, of course you can say MI plus 1 plus 2, but let's not simplify that way. This part over here, Ni plus 1, matching here, is exactly Ni prime. So by equation 2, it's going to be Ni prime plus 1. All right? If you're somehow missing the small details, that's okay. You can just review maybe later. But just get the big picture right. When we get to the final step, before we conclude the proof, you have to somehow rewrite different measures and also use the inductive hypothesis. So what we got eventually, Ne prime equals Ni prime plus 1. Okay? That's how we conclude the proof. Now it's done. All right, so that's the complete walkthrough about how you can do mathematical induction on trees. That's something you have to worry about for this course. In 3101, we'll talk about how you can apply the same proof technique on graph. All right, guys, any questions? Just in general. Of course, you got to study for this, and let me know if you got any question about the details. Okay? You might be given something similar, right? You just have to make sure you can maybe reach out to other resources to see mathematical induction on trees in general. You'll find similar pattern, just similar steps. Okay. Okay. If no questions, we can move on. Okay. Okay, this is done. And then I just want, actually I want to discuss one more example about proper binary tree. Okay. No, we are now done with the slide number 36. Okay, that one's done. So you can also see the proof as well on the slides, but I would say maybe go with the iPad notes. I think that one's more like a structure and visualized. But you can go with the slide too. You know, they're both correct. It's kind of up to you. All right, binary tree applications. Okay, one is about decision diagram. You know, you can think about every internal node is about making some decision, either true or false. So that's why it's binary. Either true, go to the left child, or false, go to the right child. Right? You can look at an example. It's a very common one. If you are doing machine learning, for example, some of the training model would be based on decision tree. That's actually the foundation for that, right? Of course, we wouldn't go into details about how you can process decision tree, but that's one example. Another one I can dive a little bit deeper is about how you can represent arithmetic expression using binary tree, okay? Let's look at this. So over here, let's say, for example, if I only look at, so let's think about how you can interpret the tree. Now think about the external nodes first. I got 3, 1, 3, 9, 5, 2, 3, 7, 4, and 6. So these are all the external nodes. External nodes will be representing numerical constants. External nodes denotes numerical values, numerical constants. On the other hand, I have also internal nodes: minus, divide, multiply, plus, minus, plus, multiply, and plus, and also minus, right? So these are the operators or operations for numerical values. Internal nodes, more specifically, all these operations are binary, which means you require exactly 2 operand, right? Binary numerical operators. And not surprisingly, the consequence for the binary tree is it's proper, because now you can see that for every internal nodes which represent a binary operation, you got exactly the 2 operands. So that should be a proper binary tree. Okay? So that's a nice consequence of this particular application. Okay? So here, since we talk about binary numerical operators, so the consequence is it's a proper binary tree. Right? So here we're assuming that we only got binary operators like a multiply, plus, divide, etc. Okay? But what about in general? Like the question over there. If you want to handle numerical expressions in general, does it have to be proper? Is there any missing cases for numerical operation that might make this tree here not proper anymore? I'll give you a little bit hints. Okay? For example, you can see that if you only look at this subtree, that represents, for example, 3 plus 1. Right? You can see the plus here, and 3 and 1. 3 plus 1. Right? And also here, it represents 7 minus 4, and etc. Right? We're going to see exactly how to systematically traverse the tree in just in the next page. But that's about the individual expression you can represent. Is there any operator that's going to be not exactly binary? Anybody? Can you think of any example? Yeah, go ahead. A power, you mean, for example, 2 to the power of 3? But in that way, in some way, that's also binary, isn't it? Because if you think about 2 to the power of 3, you need to have the base and also exponent. You still got 2 required. Good try. Okay. How about this? When I say minus 4, the minus operator over here is applied directly to whatever value I have to make it, to change its sign from positive to negative. That one is a unary operator, right? So this is a unary operator, okay? So let's say, for example, if I got minus 5 multiplied by 4, let's say, how should the tree look like? Overall, it's a multiplication. So I start with this internal node over here, and then I got left subtree and right subtree. The right subtree will just contain 4. The left subtree over here will be the subtree representing minus 5. But minus 5 here is a unary operator applied to 5. So minus over here, and then you just got 5. Right? So this is general because we want to be able to also handle negative values. But if you look at the tree over here, is it proper binary tree? No, it's not, because this internal node here has only one child, not 2. All right, so that's the point I'm trying to make. All right. So this one here is not proper binary tree. So whether or not you really want to maintain your binary tree to be proper when you want to represent numerical expressions, think about whether you want to have unary operators, right? That's a decision you have to make. Okay. Questions? Yes?
Could you just say like 0 minus 5?
Sorry, say it again.
Use 0 and 5.
0?
0 minus 5.
0 minus 5. How do I represent it?
No, like, what if you just did that instead? That's simple.
Well, it's more like, okay, I see what you mean. So you're saying, okay, let me just go back. You're saying rather than using this one here, right? Okay, I see what you mean. Let's make the point clear. I agree with you. This one here, you could have said 0 minus 5 and multiply by 4. That's one possibility, but you cannot force the user of your program to always specify 0 minus 5 as opposed to minus 5. We want to allow the flexibility or variety of ways to write equivalent expression for the user. So that's why I said it's really a decision you have to make. If you always force the user to really write negative value as 0 minus something, that's one way to go. But your user may not like it. They may just want to say, why can't I just write the negative sign here? Right? It's a choice. Okay. Next topic, traversal. Okay. All right, so now this will be the final topic for binary tree, okay? And then we can do a little bit of intermediate recursion today, okay? Let's see how far we can go. So, and then we go on to slide number 39, tree traversal. Let's see what's the general purpose, and then we talk about the kinds of a traversal we can have on the tree. So a traversal would just be, you want to systematically visit all the nodes in the tree, right? It's like if you got an array, the traversal mechanism could be you go all the way from left to right, or from right to left, right? It's about traversal, but for tree, you got more variety for you to think about, okay? So you can visit all the nodes, and then you can maybe try to print out everything, or you can try to see if they will satisfy certain property. For example, are all the nodes positive? Or if I have any nodes that's within certain range. Okay, so there are different purposes for you to do the visit. Okay, and this one here, accumulate. For example, I want to calculate what's the average value for all the nodes in the tree. That's also another way, right? You want to accumulate the sum of all the elements and then divide it by the number of nodes in the tree. So that will be something you have to do for assignment number 3, right? So you got to make sure you also know how to do that, right? And there are 3 traversal orders, right? Let's now go over the big picture, and then we're going to do example to convince you, okay? The first one here is about pre-order, okay? Pre-order means I want to visit the current node first, and then all its children. Parent first, and then children, okay? That's the principle, but we'll get to see exactly how to do it. You will see something like a pseudocode, right? So we say, if I want to do a pre-order traversal starting from node n, first of all, visit n itself, like a parents, and then visit individually its children recursively, right? So notice the order. The opposite way will be post-order. That means I want to visit all the children recursively one by one before I visit the parents, right? The opposite. So here, I say I want to visit all the children recursively, and then I want to visit the current node. We'll see example. Now, the third way is important to note. Pre-order, post-order, they are applicable to general trees, which means it doesn't matter how many child nodes you have. That's why you have a for loop. But the third kind of traversal called in order is only applicable to binary tree. You cannot apply in order traversal to a general tree with, for example, more than 2 children. All right, that's something you want to keep in mind. Okay. So in order is recursively visit the left child, and then the parents, and then recursively visit the right child. Right? Left child, parents, and the right child. You can revisit this slide here, maybe after you study the example. Let's just do from example to gain the intuition. Okay? Let's see. All right, let's revisit our family tree example here. Let's start with pre-order and post-order. The reason is this particular family tree, you can see it's a general tree. It's not binary. For example, this internal node here, we got 1, 2, and 3 children. It's not binary anymore. So that means only pre-order and post-order are applicable, not in order traversal. Okay? And let's work it out. So you can see the same example. What will be the difference when you try to do pre-order versus post-order? Okay? Let's start with the pre-order. And the pre-order is, let's say we want to do pre-order starting from David, let's say. Okay? So let's say I want to do the pre-order starting from David. Let me say PO. Oh, let me say pre-order of David. The starting point. Okay? And according to the principle, we are simply going to visit this node first, and then recursively do pre-order traversal on each of the child nodes for David. Let's write it out. Okay? So that one is going to be David, which will be the starting point. And then we want to recursively pre-order traversal on the subtree. Okay? This will be the first subtree, and this will be the second subtree. Okay, because he got only 2 children. So we say David, and then we're going to do a pre-order traversal on Ernesto, followed by the pre-order traversal on Chris over here. So that's going to be a pre-order traversal on Chris. So what's so good? Right? You want to see the big picture. You're saying that if I want to do pre-order traversal starting from here, parent first, and then recursively do the first child, and then recursively do the second child. The pre-order traversal for Ernesto will be the base case. There's only one node. It's like an external node. So it will be just Ernesto. So that one there will be just Ernesto. What about the pre-order traversal of this particular subtree? We're going to do something very similar. You have to visit Chris first, and then recursively do pre-order on the first child. Recursively do the pre-order on the second child. Right? Let's follow that. Okay? So what we do is we're going to have Chris, first of all, followed by 2 recursive call. Let's say we do number 1 over here. And let me do a little bit bigger. Okay? There's one here. This will be the pre-order traversal on Elsa, right here. Okay? So this will be the pre-order traversal on Elsa. Okay? And then we're also going to do the pre-order traversal on Anna, which will be right here. Okay? Followed by the pre-order traversal on Anna. Okay? And we can, since we're doing this visually, so let's pick the simple one. Pre-order traversal on Anna will be just Anna, right? It's external. Anna. What about the pre-order traversal for Elsa? Right? Again, it's going to go recursively. So we're going to go for Elsa first, the parents. And then we're going to do pre-order traversal for the 3 child nodes. One here, and also one here. Okay? So it's going to be 1, 2, and 3. Okay? Pre-order traversal for Shirley, pre-order traversal for Vanessa, and pre-order traversal for Peter. Okay? And each one of them is simply base cases, right? So we got Shirley, we got Vanessa, and we got Peter. And if we combine the orders together, what do we have? Right? You can see this will be David, followed by Ernesto, followed by Chris, followed by Elsa, and then Shirley, Vanessa, Peter, and also Anna. Okay? If you look at the tree again, okay? Pre-order traversal goes like this. David, Ernesto, Chris, Elsa, Shirley, Vanessa, Peter, and also Anna. That's the pre-order traversal. Questions? Why don't we try one exercise with you right away? Can you do pre-order traversal here? Give it a try. I'll start you with, why don't we say pre-order traversal? Let's say starting from here. So this one got to be visited first, right? And then we have to do pre-order traversal on this subtree, followed by we do pre-order traversal on this subtree. Oh, sorry. Okay. Let's give it a try, right? If you're not exactly sure, just give it a try. It's okay to be wrong. And then we're going to go over answer, and then we'll go to post order. Once you get the idea for one, the other two are not that bad. Right? Just gonna get yourself used to thinking recursively, and also about what's the order of visiting the subtree. That's really the essence for distinguishing between these three traversal. Okay? Okay, I'm writing down my answer as well, but meanwhile, you can also give it a try, and I will give you some like a comparison. Okay. All right, that's a standard answer. You can maybe try to redo it after today, but this is how I would double check the answer at the end. Okay. First of all, you can see that I start with the minus sign, which will be the parents right here. And then I go for the left subtree. So that means this part over here would be the pre-order traversal result for this subtree. Right? And also this part over here for the subtree, the pre-order is going to give me this. And let's go a little bit more inside for the even deeper subtrees. Okay? And for this one here, you can see the divide right here. And then the pre-order for the left subtree is going to be this part over here. The pre-order traversal for the right subtree is going to be this part here, and so on. Right? You can try maybe deeper subtree yourself. Okay? And then if you look at the plus over here, that's the plus we have. And then we got the left subtree right here. The pre-order traversal is going to be this part. And then the pre-order traversal for the right subtree for the plus is right here. Right? You can see that, right? Gradually. All right. Any question about pre-order? Okay. Why don't we do post-order? Very similar. So for the post-order, we're just going to make sure we recursively visit all the child nodes before we try to do the parents. All right. That's the principle. Okay. So why don't we try that? Okay. So now, let's say we want to do post order, let's say from, again, David. Right? David is going to be the parents. So we're going to put David last. And then we're going to put the post order traversal for the first child and the post order traversal for the second child. Okay? So think about here is going to be the post order for Ernesto. And this part here is going to be the post order for quiz. After these two post orders, we're going to have David at the end, right? That's the post order. Okay? Post order for Ernesto, the same as before, is going to be just Ernesto, base case. What about the post order for quiz? Quiz, first of all, should really appear at the end. And then we got left subtree, first child, first subtree, and second subtree. It's going to be the post order for Elsa. Post order for Elsa. And also the post order for Anna. Right? I'll put Anna here. And this part here is going to be the post order for Elsa. So Elsa is going to be put right here. Right? And then post order for Shirley, post order for Vanessa, and also post order for Peter. Right? So it's going to be 1, 2, and 3. 1, 2, and 3. So post order for Shirley, post order for Vanessa, and post order for Peter. So Shirley, Vanessa, and Peter. So the final outcome for the post order goes like this. Okay, so we start with the post order traversal. So that'll be Ernesto, Shirley, Vanessa, Peter, and then we got Elsa, and then we got Anna, and we got Chris, we got David. Okay, that's the final result. Okay, post order. Okay. Okay. Let's now see this, and I'll give you some exercise, which we'll start with on Thursday. Okay. Thinking this way, we start from here. However, the starting point will be the last point you will visit. It's more like a stack idea, a little bit like that. Okay. So we're going to go for Ernesto here, and then in order to post-order traverse this tree here, I need to somehow traverse this one first. Shirley, Vanessa, and Peter. And then the parents, Elsa. So this subtree here is done. And then I'll do Anna here, so the second subtree is done. And then I go to Chris. And finally, I go to David. One more time. Ernesto, Shirley, Vanessa, Peter, Elsa, Anna, Chris, and David. Okay? Try to look at the pattern over here in this simple example here, and then we'll start with this solution here. Given this example tree, given this example binary tree here, try to do post-order traversal. Okay, important exercise, and you will definitely be asked questions somehow related to it in the test or the exam. Right? Try this one here, and then we'll look at your answer together on Thursday. Questions? Okay, thank you. I'll see you on Thursday.